Everybody, and welcome to the second video in the playlist Database System Concepts, where I review the textbook, and today's chapter is going to focus on relational databases. So this is a relatively short chapter, only a few sections, so the video should be pretty quick, and it's mostly a review. A lot of it was covered in chapter 1. So section 2.1, structure of relational databases. Some basic terminology. We have relation, tuple, and attribute. Relation is synonymous with table, tuple is synonymous with row, attribute is synonymous with column name. These are just mathematical terms, so that's what we use. Secondly, in the most basic implementation of a relational database, we have the domain of an attribute, right? So the set of all possible values for a particular attribute. For example, let's say a student name is an attribute. The domain, all possible names a student could have, is atomic. Now, what does this mean? This means it is single, right? It's not itself a set of different values. So, for example, the student name wouldn't be, Jonathan, comma, Johnny, comma, John. It wouldn't include his nicknames as well. However, you can have a different implementation that extends relational database that does keep it so the domain of an attribute can not be atomic if you want. Lastly, we have null values. Now, if you're familiar with null in Java, or I think it's none in Python, right? These are values that signify emptiness, right? Nothingness. Not zero or false, but nothingness. The absence of a value. Now, null is pretty bad design-wise to use in a relational database or in a programming language, because the meaning is always very unclear. So it would be best if you stray away from using null values, but in some query languages they are an option. All right, section 2.2, database schema. So some common confusion between a schema and instance. Just to be clear, a schema is the abstract representation of the database, right? I have a schema, I have a student table, I have a course table, whereas an instance is the specific student table or the specific course table, right, with all the values listed out. And remember, you could have a student table and delete it and make a new student table, right? So that would be a different instance. Basically, it's a snapshot of the data in the database at a specific time. The book explained this using a variable analogy. I'll quickly go over it. Basically, a relation or a table is equivalent to a variable, and a schema is equivalent to a type definition of a variable, right, like integer. And because it's defining the specification of the variable, and the value of a variable, right? Since it's instantiated, represents the instance, basically. And what a schema is, just to give a precise definition, is all the attributes of an entity and their domains. Section 2.3 covers keys. Okay, so we have three types of keys. Super key, candidate key, primary key. Okay. Now, the way they are listed on the screen, so super key, candidate key, primary key, that's the order in hierarchy. So we have this thing called a super key. Now, what is that? It's a attribute within a relation that is unique. Okay. So let's say we have a student ID. That'll be our super key for now, and a student name. So people can have two students can have the same name. Therefore, we have a student ID attribute so we can get some uniqueness and not be confused among, two different tuples of the relation. Now, it's important to remember that even though a superkey doesn't have to be one attribute, it can be the union of many. For example, even though student ID is a superkey, right, because it's going to be unique, a student ID and a student name can, those in conjunction can also be a superkey, right? So any superset of one superkey is also a superkey, or any superset of a superkey is a superkey. Now, a proper subset of a superkey is a candidate key. For those of you who don't know set theory, a proper subset means it's an element contained in the set but not equal to the set, or a collection of elements within the set but not as many as the set or the same set. So for example, the candidate key of the superkey student ID student name is student ID, because student ID is the most minimal superkey you can get, let's say. Now, a primary key is synonymous with candidate key. In a way, it just means the user-defined candidate key. So when a user is making a schema, he'll say student ID and label it as the primary key. Now, we also have notion of foreign key. What does that mean? Well, if you have two relations, right, each having primary keys, you can reference in one relation as an attribute the primary key of an attribute in another relation, and therefore you have a reference to that table. So this relation 1, right, that has the primary key of another relation would be called the referencing relation, and that would be called the foreign key within that table. And then in relation 2, that would be the referenced relation, and that would be the primary key for that relation. Does that make sense? And it's important to note that sometimes you can't go back and forth. In other words, one relation can reference another with a foreign key, but the other relation can't always reference the first relation with a foreign key. For example, you could have a table with, let's say, x, y, and z, all right, and as attributes, and another table, x, y, z, a, all right. Now, the first relation, x, y, z, as attributes, those in conjunction represent the primary key, whereas in the second relation, x, y, z, a represents the primary key. So relation 2, x, y, z, a, can have a foreign key to relation 1. However, relation 1 can't have a foreign key to relation 2 because it doesn't contain part of the primary key, right? The relation 2 has more data that makes it change, right? That it maybe the first relation, can get away for whatever its meaning is conceptually, right, in the application, that it doesn't need all these attributes, and it could just be unique based off of x, y, z, while the other one needs an additional parameter, a, to make it unique. So you could have one reference the other, but not the other way around. And this is known as from a previous chapter, we said referential integrity constraint. Although there's different types of referential integrity constraints, this is the most basic one, a foreign key. So in schema diagrams, you can represent different relations and their attributes, as well as primary keys and foreign keys. And foreign keys would, be drawn with arrows pointing to a different relation's primary key, right? So you can visually see all the primary foreign key relations as well as the attributes for every relation. And in the most basic schema diagrams, and usually most of them, this is all that will be shown. All right, section 2.5, relational query languages. They talk about SQL being both procedural and non-procedural, like most languages these days. However, if you want to get, they say, pure query languages, you use either relational algebra, which is a procedural DML, or you use relational calculus, which is a non-procedural DML. Now, relational algebra uses basically propositional logic and set theory, and relational calculus does as well. So relational algebra, you could say select this from this relation and that from that relation, and that will form a new relation, and then you transform that relation to another relation until you get what you're satisfied with. All right, in relational calculus, and I'm sure they're going to have a chapter explaining this more in depth, but it's pretty easy if you just, by the way, look up relational algebra, relational calculus. Very simple. If you walk through a few examples and you have a background in propositional logic and set theory, you'll understand it in 5 seconds. And relational calculus comes in 2 forms, and these are basically the same thing, by the way. Tuple relational calculus and domain relational calculus. All this does is basically select, for tuple relational calculus, you do the tuple dot attribute such that the tuple in this table has this quality, right? So you're not really specifying, the intermediary, like, hey, take this relation, form this new relation, and then give me that, right? You're just saying, hey, select this tuple for me. And then in the domain relational calculus, you're just doing select these 2 attributes. Instead of working with tuples, you're working with attributes. And lastly, section 2.6, relational operations. So they briefly cover the definitions of join, natural join being, a subset of join, the alternative to natural join being inner join, although they don't cover it. Cartesian product, union, intersection, and set difference. So if you're familiar with set theory, this is all review. I shouldn't need to explain this. However, real quickly, I'll explain it in the context of relational data models, relational databases. So, join is basically joining 2 tables by a specific column. Now, depending on the query language, let's say the specific column doesn't necessarily exist. A possible implementation of the query language is when you do join, but there's no common column between the 2 tables, it'll just form a Cartesian product. So a natural join is when the one table or a column from one table and a column from the other table are exactly the same, and you join on that column, right? And all the data just gets appended to one another. Like let's say tuple A from relation A that has attribute C is appended to tuple B in relation B with attribute D, where C and D are the same, right? And the whole table gets appended like that. The other join would be inner join, where basically you specify a condition on which to join on instead of joining on a whole entire column. Cartesian product just gives you every possible pair of the 2 tuples for every tuple within the relation, right? So let's say you have 2 tuples in relation A and 2 tuples, or let's say 3 tuples in relation B. In relation A, you would have tuple A with tuple, 1 from relation B. You would have tuple A with relation 2 from B. You would have tuple A with tuple 3 from relation B. So that's already 3. And then you would have tuple B from relation A with tuple 1 from relation B, and then tuple B from relation A with tuple 2 in relation B, right? So you do every combination. That's Cartesian product. Union, you're just adding, it's basically you append one table to the other table and eliminate duplicates. That's it. Some languages have union all, which I'm pretty sure just does union, except doesn't remove duplicates. Intersection finds where two tuples are the same within two different tables, right? So you're intersecting in two tables, and let's say the result set is cardinality 5, which means 5 tuples were returned. That means 5 tuples from relation A and relation B were the same in both relations. Set difference, also known as, like, let's say the set difference of B, and you have relation A and B, that would basically be, or the set difference of a B with A is basically just the complement of B union with A. To give you, I don't have the best diagram for this. Let me, there. So this is set difference right here, visually. All right. Now, so basically what that does is it gives everything in table A that's not in table B, or vice versa, depending on the operands. And that is it for this chapter. A very short chapter. In the next chapter, we will be introducing the SQL language, all of its syntax. We basically introduce the semantics in this chapter for SQL. So stay tuned. Have a good day. And make sure to subscribe to see the rest of this textbook review, as well as others I will be posting in the future. Leave a comment on what you think or what other textbooks you want me to review, and make sure to give a like. Thank you.